Now that you understand how exactly a convolution layer works, including the bias term and activation function, we can now consider the architecture of a convolutional neural network and why it's that way. So, as a little bit of a history lesson, modern CNNs essentially all originated from the same model, the LeNet. This is named after Yann LeCun, one of the original deep learning pioneers, along with Geoffrey Hinton and Yoshua Bengio. What we're going to do in this lecture is just start with what the architecture is, and then go through it piece by piece so that you understand why it is the way it is. Okay, so let's look at a typical CNN. A typical CNN has two stages. The first stage is a series of convolutional layers. Importantly, these convolutional layers are usually followed by pooling layers, which is another type of layer we'll discuss shortly. The second stage is a series of dense layers, also called fully connected layers. These are just a regular feed-forward neural network as you saw in the previous section. If you recall, I said in the previous section that neural networks have this hierarchical structure. Each layer is always looking at features that were found in the previous layer. So you can even think of the first stage as just another feature transformer. It's a feature transformer that specifically works on images and finds image features. Then, once it's found those image features, it passes those into a neural network, and then the neural network does what it does best: nonlinear classification or regression. So let's have a closer look at the convolutional stage. Now, I just added a new layer without really explaining it, the pooling layer. Why would we want to do that? At a high level, pooling acts as a downsampling operation. What is downsampling? That's when you make a smaller image out of a bigger image. So imagine your image is 100 by 100. After pooling, if the pool size is 2, then you would get a 50 by 50. That's downsampling by 2. Let's go over mechanically how this works, and then we'll explain why it works and why we would want to include it in our neural network. So there are two kinds of pooling: max pooling and average pooling. Choosing which one to use is, as you probably guessed, a hyperparameter choice. Let's talk about max pooling first, since I think this one's a bit more common. The best way to see how it works is by example. So if we start with an image, let's say it's a 4x4 and contains these numbers: 1, 2, 3, 4, 5, 6, 7, 8, 16, 15, 14, 13, 12, 11, 10, 9. So just the numbers 1 to 16, but organized non-sequentially. What max pooling will do is take each 2x2 square, of which there are 4, and just return the maximum value in each of those squares. So the max of 1, 2, 5, 6 is 6. The max of 3, 4, 7, and 8 is 8. The max of 16, 15, 12, 11 is 16. And the max of 14, 13, 10, 9 is 14. So the output image is 6, 8, 16, 14. As you might have guessed, average pooling is similar, but instead of taking the max, we take the average. So for the same input image, we have the following. The average of 1, 2, 5, and 6 is 3.5. The average of 3, 4, 7, and 8 is 5.5. The average of 16, 15, 12, 11 is 13.5. And the average of 13, 14, 10, 9 is 11.5. So the output image is 3.5, 5.5, 13.5, 11.5. Now that you know how pooling works, let's talk about why we should use it. The first advantage of pooling is practical. If we downsample the image shrinks, and therefore we have less data to process, less multiplications to do, and of course that will speed things up. But the second and more important advantage has to do with image processing itself. Recall this idea of translational invariance. This is the idea that I don't care where in an image the feature occurred. I just care that it occurred. For example, both you and I can recognize this as an A. We also recognize this as an A. It doesn't matter where I put the A on the screen. So translational invariance is important from a biological point of view and how we as humans learn. We don't have to learn how to recognize A's at each point in our field of vision. Once we know what something looks like, we can recognize it, no matter if it's up, down, left, or right. So what is max pooling doing? Well, consider a small 2x2 box. Remember that convolution tells us whether or not a feature has been found. It's a pattern finder. So imagine that in this 2x2 box, I have these flags. Pattern found, not found, not found, not found. So it's a high number, and a small number, and a small number, and a small number. The pattern being found returns a higher number. So when I take the max, it says the pattern has been found. That's good because it tells me that the pattern has been found without caring where it was found. Average pooling is the same idea, but I think max pooling is a little more intuitive in this regard. As a side note, keep in mind that in this lecture, I've assumed that we're using a pool size of 2, and that at each pooling layer, we select boxes which are 2 spaces apart. Now, pooling layers have some flexibility in this regard. First, it's not necessary for the pool size to be the same in both directions. For example, you could look at a 2x3 box or a 3x2 box, although generally that's unconventional. Second is that it's possible for the boxes to overlap. The hyperparameter that controls this is called the stride. It tells us how many spaces to move the pooling box for each output. Previously, we looked at the situation where we had a pool size of 2x2 and the stride was also 2. This is a pretty common scenario. If you had a stride of 1, then our 2x2 box would overlap. This is not really too common. So while you have these options, which I want to make you aware of, they're usually not changed too often. So what you see in this lecture is what we do most often. We use a pool size of 2 in each direction, and we have a stride of 2 so that we don't have any overlapping boxes. So now that you know what pooling does and why it works, let's discuss why the convolutional part of the CNN is organized the way it is. Why should we have a sequential pattern consisting of a conv layer, followed by a pooling layer, followed by a conv layer, followed by another pooling layer, and so forth? If you recall, I told you earlier that one cool thing researchers discovered is that CNNs are able to learn features hierarchically. So the initial layers end up learning basic strokes, the next layer ends up learning individual facial features such as nose, eyes, and lips. The next layer ends up learning whole faces. The key point to keep in mind is that after each pooling, the image shrinks, but the filter sizes generally stay around the same. Common filter sizes are 3x3, 5x5, and 7x7. Generally speaking, they are much smaller than the input image. But what happens as the image shrinks as it passes through each layer? Well, let's suppose we start with a 32x32 image, and we have 4 convolutional and pooling layers. Let's assume we do convolution in same mode so it doesn't change the size of the image. And let's assume all our convolution filters are size 3x3, although this doesn't come into play just yet. In this case, after the first convolution and pooling, the image shrinks down to 16x16. After the second convolution and pooling, the image shrinks down to 8x8. After the third convolution and pooling, the image shrinks down to 4x4. And finally, after a fourth convolution and pooling, the image shrinks down to 2x2. What happens after this is still a mystery, so let's just leave that for now and focus on the image shrinking. As you can see, if you take a 3x3 filter and place it over a 32x32 image, it occupies only a very small portion of the image. In other words, it's looking for very tiny patterns to match, like for example, simple edges and strokes. Then the image becomes size 16x16. Now all of a sudden, the 3x3 filter takes up 4 times as much space in the image. It takes up twice as much space in each direction, and 2 times 2 is 4. In any case, it occupies a much larger portion of the image relative to the first filter. So now it's looking for patterns which take up more space on the image, patterns like nose, eyes, and lips. Next, we get to an 8x8 image. A 3x3 filter occupies almost a quarter of the image. After that convolution and pooling, we get a 4x4 image. Now, a 3x3 filter takes up most of the image. So what have we learned? We've learned that in a convolutional neural network, convolution and pooling results in two things which are corollaries of each other. First, the image input shrinks. Second, since filters generally stay the same size, the filter looks for larger and larger patterns in the image. This is what leads to the CNN learning hierarchical features of the input. It first learns things that are relatively small compared to the total size of the image. Then it learns to find bigger patterns and so forth. The last concept regarding the convolutional layers we have to think about is, are we not losing information at every layer if we shrink the image? And the answer is yes, that's true. We are losing spatial information because the image keeps shrinking. We're saying we don't care where in the image the feature was found, just that it was found somewhere in the image. So we're losing information about where it was. But there's another component of the convolution process we haven't considered yet, which is the number of feature maps. Again, we have a general pattern to follow, which is that while the size of the image generally decreases, the number of feature maps generally increases. In other words, I don't care where the feature is found, I just care that it was found. But I do care about different possible features I can find. So while you're losing spatial information, you're gaining information in terms of what features were found in the image. One last note on this convolution and pooling pattern. One of the hardest things to grasp for new students in deep learning is that we have so many choices. We call these hyperparameters. Previously for ANNs, we looked at the learning rate, the number of hidden layers, and the number of hidden units. But now with CNNs, we have a ton of more choices. With convolution, we have to choose the filter size, we have to choose the number of feature maps, we have to choose the pool size, and so forth. But luckily, I think this is one instance where there's a general pattern that most people follow, so you're not going in completely blind. So stick with these guidelines, and you can be sure that you're at least doing things per accepted convention. That is, choosing small filters relative to the image, like 3x3, 5x5, or 7x7. Another guideline is to repeat the pattern, convolution followed by pooling. Another guideline is to increase the number of feature maps at each convolution. So you might start with 32, and then 64, then 128, and maybe 128 again. The best way to learn about how other people are doing it is to read lots of papers and check out which hyperparameters they selected. Generally, you'll find that this is the pattern followed by most convolutional networks. Next, I want to mention something a little funny, but in fact, pooling is sometimes not what we are going to end up using in our CNNs. Researchers have found that we can do something similar, but which is more efficient and sometimes works just as well. In particular, recall that for pooling, we have this concept of stride. That tells us how far apart each box should be when we take the max. In fact, convolution has a stride option as well. So in this animation, you can see how convolution works with stride. Remember, convolution just means multiply and add with a sliding window. When we have convolution with a stride parameter, the stride tells us how far apart each window should be. And of course, our intuition tells us that if we use a stride of 2, then the output image length will be half of what the input was. In other words, we get the same reduction in size by using a strided convolution instead of convolution followed by pooling. The intuition behind why this works is that if you consider what an image looks like, an image is just large patches of stuff. What I mean by that is, each pixel is likely to have a similar value to its neighboring pixels. For example, suppose I'm looking at a red car. I find a red pixel. Now ask yourself, is the pixel above that also red? Yes. Is the pixel below that also probably red? Yes. The same can be said of the pixel to the left and to the right. That's just the nature of images. Pixels near each other are often very highly correlated. You won't have this random jumping around of pixel values because something like that wouldn't look like an image at all. That would probably just be noise. And so using a stride of 2 simply means having your filter skipping every other pixel. It's saying we don't care what those skipped pixels are because they probably are very close to the pixels we were already looking at. So to summarize, the convolutional part of our convolutional neural network now looks like this. We can have a series of strided convolutions, all with approximately the same filter size, with increasing feature maps at each layer. Or we can have a series of convolutions followed by pooling, again all with approximately the same filter size, and with increasing numbers of feature maps at each layer. The last part of this lecture will focus on the second half of the CNN, which is the feed-forward neural network part. Now there's not much to discuss here, except that we have to consider the shape of an image is not appropriate for a dense feed-forward neural network. Remember that when an image comes out of a convolution, it's going to be three-dimensional, height by width by number of feature maps. But a feed-forward neural network takes in a feature vector, a one-dimensional object. Luckily, we've already discussed how this works. We can turn a 3D object into a 1D object using the view function in PyTorch. One alternative to the flattened layer, which I really like, is the global max pooling layer. This is a little different from the regular kind of pooling we discussed earlier. Consider the question, what if we have different sized images? The largest source of images is the internet. Generally speaking, images we find on the internet are not all the same size. So it makes sense to wonder, is it possible to build a convolutional neural network that is capable of handling different image sizes? And the answer is yes, using a global max pooling layer. Let's consider first why a simple flattened layer would not work. Suppose again we have an input image of size 32 by 32 and 4 convolutions. Assume again we use convolution in same mode and we have a stride of 2. So after the first convolution we get a 16 by 16, after the second convolution we get an 8 by 8, after the third convolution we get a 4 by 4, and after the fourth convolution we get a 2 by 2. But now let's say we have an input image of size 64 by 64. In this case the output after 4 convolutions would be 4 by 4. Let's say for simplicity's sake, the number of output feature maps is 100. Then, for the 32 by 32 image, doing a flatten operation would yield an output of size 2 by 2 by 100, 2 times 2 times 100, which is 400. For a 64 by 64 image, doing a flatten operation would yield an output size of 4 times 4 times 100, which is 1600. And of course, a feed-forward neural network is not capable of handling vectors of different sizes. Now, let's consider how global max pooling works. The idea is simple. If our input image is h by w by c, then the output is 1 by 1 by c, or equivalently just a vector of size c. In other words, it takes a max over the entire image along the spatial dimensions over each feature map. Since we have c feature maps, we end up with what is essentially a one-dimensional vector of size c, since the one dimensions are redundant. This follows the same general idea of pooling, where we're saying, I don't care where in the image the feature was found, just that it was found somewhere. Global max pooling is the extreme of this, saying that the feature can be found anywhere in the entire image, across the entire height and width. Since the output is always a vector of size c, it does not depend on the size of the image, meaning that it allows the network to handle images of any size. As a side note, we also have global average pooling, which is just a global version of regular average pooling. The only exception to this is if your images are too small, in which case you'll just get an error when you try to run your code. For example, if your image starts out as a 2 by 2, then it's not possible to reduce the dimensions by half 4 times. You'll notice this happens if you do something like add too many convolutions to your neural network. Alright, so let's summarize the basic architecture of a modern convolutional neural network. The first stage is a series of strided convolutions, or optionally, convolution followed by pooling and repeating that pattern. In the interface between convolution layers and dense layers, we have a flatten. We also optionally have a global max pooling that reduces the image to just the max for each feature map. Finally, once we flattened our data into a one-dimensional vector, we have a regular feed-forward neural network made up of a series of dense layers as usual. And as you learned in the previous section, the activation and number of nodes for the final layer depends on the type of task being done. So if you're doing scalar regression, then you'll only have one output node with no activation function. If you're doing binary classification, you could have one output node with a sigmoid. However, for k equals 2 or more classes, you can have k output nodes with a softmax activation.